Okay, so let's try another example. So here I have kind of an example that might be applicable these days. I just kind of made it up. So again, this is a hypothetical population where 39% of the population, which is in Hardy-Weinberg equilibrium, so that means you can use these formulas, the Hardy-Weinberg equations, they have a genotype, which is little n, okay, so that's homozygous recessive, making that makes them susceptible or at risk for severe effects from infection with the SARS-CoV-2 virus, which we're experiencing these days. Now, the homozygous dominant and the heterozygotes are not at risk. Okay, so their genotypes do not make them susceptible for the severe effects from infection with this virus. Now I'm asking you to find the following things. Right, so the first one says, what percent of the population are not at risk? All right, so right now we know that 39% of the population are at risk, right? Okay, so that's what I wrote. Okay, so what does that mean? Okay, so the rest of the population is not at risk, right? So you just take 100 minus 39 equals 61. 61% of the population are not at risk for the severe effects of the virus, right? So we can convert this to a decimal, right? So this will be it can be a probability, right? So we can convert it to 0.39 and 0.61. Okay, so this is the fraction of the population that is at risk, and this is the fraction of the population that is not at risk. Now, these numbers mean something in the Hardy-Weinberg equation, right? Okay, so again, remember, we've got 39% of the population. Okay, so that's equal to 0.39. They have a genotype, which is this right here. That's homozygous recessive. So that answer goes down here, right? So I'm asking you later, what is the frequency of the homozygous recessive genotype, right? So that's 0.39, okay? Homozygous recessive is this, little n, which is equal to q squared, right? And here, the 61% or the 0.61 represents both the homozygous dominant and the heterozygotes. So this actually represents these and these. Okay, so that's adding them together. So we can't really do anything with that right now. Okay, so what we need to do is first, let's go ahead and move to the next question, B. We have what is the frequency of the recessive allele, right? So we know that the homozygous recessive genotype is 0.39, okay? So that's q squared. What we want to do is find q, right? So this is equal to q. What do you want to do? Right, so now you want to take the square root of q squared, which is the square root of 0.39, which is, let's see here, what did I calculate that? That is 0.624. Okay, so we know q. Now we can find p, right? So remember, p plus q equals 1. These are the sum of the frequencies of the alleles in that population. So if we know that q is little n, what we want to do is find big N, right? And the sum should total 1. So now what we want to do is, this is what we're trying to find right here. We're going to take p plus n, which is 0.624 equals 1. So then 1 minus 0.624 is going to equal, so p equals 0.376, right? So that's big N. Now we can find the genotype frequencies. So now we want to find this right here, okay? And then we want to find this right here, okay? And we already found this. So The homozygous dominant, the frequency of them, are going to be the following. So we take p, so that's p squared. That's the same thing. So that's like p times p, because p is the frequency of the dominant allele. And we're just calling this the dominant allele because it says it's the dominant allele, right? So let's see here. We have p squared, which is equal to 0.376 squared. Right? So 0.376 squared turns out to be 0.141. And then we want to find the heterozygotes, right? So that's 2pq. And remember, p is the frequency of the capital N, right? So that's the dominant allele. And q is the frequency of the recessive allele. Okay, so now we want to multiply 2 times 0.376 times, let's see, we have 0.624 for the frequency of little n, 0.624, and that comes out to 0.469. Okay, so 0.141 plus 0.469 plus 0.39 should equal 1. So that's going to come out very close to 1. All right. So we got through that one.